Well done for completing 30% of the course. In this section, we will show you how electricity and magnetism are linked. It's quite a complex module, so take your time to understand the basic ideas before moving forward to the rest of the course. The aims of the course today are to establish the relationship between electricity and magnetism, show how we can use electromagnetism in useful ways, introduce Fleming's left-hand rule and explain how to use it. Let's now look at a magnet. A magnet has a north pole and a south pole. A magnetic field is continually generated which flows from the north pole to the south pole. If we bring two magnets near to each other and the poles are opposite, i.e. north pole to south pole, the magnets will be pulled together, i.e. they attract each other. Here we have that situation, two magnets with north and south poles. As they come together, they stay together, they're attracted. If we now bring two magnets together and the poles are the same, north pole to north pole or south pole to south pole, the magnets will be pushed apart, i.e. they repel each other, as shown. We can use attraction and repulsion effects to create mechanical energy from electrical energy. Let's now look at a coil of wire. If we wrap a conductor into a coil and put an iron coil in the middle, we can create an electromagnet. Let's now connect a DC circuit to the coil. Here we have a standard DC circuit with a battery with a positive and negative, and a switch to turn off the positive supply. If the switch is now closed, current will flow, and the coil becomes energized. As soon as this happens, it will generate a magnetic field with a north pole and south pole like any other magnet. Here's one way we can use this electromagnetism. Here we have the coil from before, with a DC supply and a switch to turn off the positive supply. We can now add a metal armature above the electromagnet, connected to some electrical output contacts. When the switch is closed, the magnetic field pulls the armature towards the coil, closing the contacts. This device is called an electromagnetic relay and can be used to repeat a single switch signal to many other devices, or to allow a small input current to switch a much higher current device. Here is another practical example. Here we have a crane with a coil attached on a boom. These devices are used in scrapyards throughout the country. Let's now add a DC supply to the coil. Here we have a standard DC circuit with a switch turning off the positive. As the coil is energized, it becomes magnetized, which attracts all of the metal objects below. If the supply is then removed, the coil loses its magnetism and the objects fall. Let's consider a single conductor. Here we have a conductor or wire. When we pass direct current or DC through a conductor, a magnetic field is produced, which is perpendicular, i.e. at 90 degrees to the current flow. The higher the current level, the stronger the magnetic field. If we now introduce another magnetic field near to the conductor, it will physically move due to the two magnetic fields interacting. So here we have a bar magnet creating a magnetic field. The conductor will then move. The direction of the movement when these interactions occur can be worked out using Fleming's left-hand rule. How does Fleming's left-hand rule work? The left-hand rule links the direction of the force, the direction of the magnetic field, and the direction of the current. Place your left hand as shown in the picture. The thumb represents the direction of the force. The first finger represents the direction of the magnetic field, north to south. And the second finger represents the direction of the current. Fleming's left-hand rule is a really easy way to link all three things together. Let's do a worked example. Let's place two magnets near to each other. We'll get a magnetic field flowing from north to south. Let's place a conductor inside that magnetic field and pass current through it. The question is, which way will the conductor move? Let's use the left-hand rule. Orientate your left hand as shown on the picture. The magnetic field is the first finger and it flows from left to right. The current represents the second finger flowing downwards. The force is the thumb pointing upwards. As soon as the current starts to flow, the conductor will therefore move upwards. Let's now see if we can use this effect for something useful. Here we have our two bar magnets from before. The magnetic field flows from north to south, left to right. Let's now add a conductor, looped round in a circle. Let's call it the rotor. Connect a DC supply and current will flow. Here's our DC supply connected to the rotor. The current flows down the left-hand side, across the top and back down the right-hand side. Which way will the rotor spin? Use Fleming's left-hand rule. First, we label the left-hand side of the rotor the left conductor and the right-hand side of the rotor the right conductor. Using Fleming's left-hand rule on the left conductor, the current is going upwards, the magnetic field is going left to right, therefore the left-hand conductor moves downwards. For the right conductor, the magnetic field is still going left to right, but now the current is moving downwards. Therefore, the right-hand conductor moves upwards. As soon as the current starts to flow in the rotor, the left-hand conductor will be forced downwards, the right-hand conductor will be forced upwards. The conductors will then move 180 degrees in an anti-clockwise direction. To make sure that the rotor continues spinning in the same direction, we need to keep the current flowing in the same direction. To do this, we add a commutator, which ensures that the flow of current on each side of the rotor stays the same direction as it rotates. We have now created a DC motor. Let's now summarise what we've learned today. A conductor or coil will generate a magnetic field when current passes through it. We can use Fleming's left-hand rule to establish a relationship between current, the magnetic field and the movement of the conductor. Finally, we can create a simple DC motor by passing a current through a conductor, then applying a magnetic field. Congratulations for completing this section, which has been quite tricky, so feel free to replay it if things don't make sense. I've attached some test questions in the course content. Please try them before going on to the next section, which will go into detail on the subject of alternating current.